Welcome to Divcasts from the University of Chicago Divinity School. For more of our podcasts and information about our terms of use, please see our website, divinity.uchicago.edu/podcasts.
But this week, I'm really thrilled to announce our speaker and dark energy. The Dark Energy Survey and the Mystery of Cosmic Acceleration. So our guest for today is Josh Frieman. He's director of the Dark Energy Survey and professor of astronomy and astrophysics here, and also a member of the Talley Institute for Cosmological Physics. Are we talking about Josh Frieman? Please join us.
Thank you. Can you hear me? Good. So it's a pleasure to be here. This is a little bit of a different venue than I'm used to, so I'm excited about it. And please interrupt me with questions, and also I'm probably going to go over, so when I see a lot of people nodding off, I'll try to wrap it up. So, the quest to understand the world around us is, of course, an ancient one, and I'm going to be talking just about a small sliver of that quest, which is the subject of cosmology. And in cosmology, we just are trying to understand the origin and evolution of the universe as a whole. And everything else is not cosmology. So I'm only going to be talking about this. And what I want to do for part of the talk is hit some points that I think every educated person should know, starting from middle school on up. And I'll use that as my way to sort of get into the subject. So basic facts about the universe. So one thing is the universe is really old. And does anyone know how old the universe is? 16 billion, yeah, close. So the real answer is older than John McCain. No, it's actually about 13.8 billion years. So you were close. So how do we know that the universe is this old? And we know because it contains old things in it. The Earth, we know from reactivity, is about 4.5 billion years. The Sun is about 5 billion years. And there are stars much older than the Sun, about 13 billion years, like the ones shown here. So this is about 100,000 stars in a cluster of stars in our own Milky Way galaxy. And these are close to 13 billion years old. So the universe is very old. That's the first thing. Second fun fact about the universe is that it's very big. Does anyone know how big the universe is?
About 13 billion years.
It could be infinite. And over here was 13 billion light years across. That was pretty close. So the part we can see, if you measured it in miles, would be roughly that many. I don't know what that is. So as was noticed, when you get to such large scales, it doesn't make sense to use human distance units like miles and kilometers. So we use things like light years or parsecs. So light travels 186,000 miles a second. So in 1 year, light travels 6 trillion miles. So that's what a light year is, it's 6 trillion miles. And so that many miles is about 14 billion light years. And just for reference, the sun, it takes 8 minutes for light to reach us from the sun, so that the sun is 8 light minutes away. The nearest stars that we see in the sky are a few light years away. So the universe as a whole, at least the part we can see, stretches a few billion light years. All right, so fact number 3, this big old universe contains billions of galaxies. So this is a shot taken from the observatory I'm going to be talking about down in Chile in the southern hemisphere. And in this picture, you actually see 3 galaxies. This is actually our galaxy. This is the Milky Way, which you can see in the northern hemisphere too at the right time of night. If you go to a very dark spot, it's that sort of band of stars across the sky. Does anyone know what those two blobs are on the left-hand portion? Sorry? Magellanic clouds, right. So if you've ever been to the southern hemisphere, you can actually see other galaxies. You can't really see any from the north. Unless you have really good eyes, you can sometimes see Andromeda. But these are two small galaxies that are neighbors to the Milky Way galaxy. And if you ever do go to the southern hemisphere, you should go out to a dark site and look for them because they're really cool. They're big. So those are some of the galaxies you can see with the naked eye. Most galaxies, the other billion plus minus 3, we can't see with the naked eye. So we use telescopes to see these. So the universe is filled with billions of things like this. This looks somewhat like our Milky Way would look like if we could get several million light years away from us. And they're typically about tens of thousands of light years across, and they contain 100 billion stars. And this was actually an image taken with the camera I'm going to be talking about. So the universe is filled with billions of galaxies. They're not just randomly distributed throughout space. They actually tend to clump together. So here's a region where there's a handful or more, tens of galaxies, all within a relatively small, meaning within a few million light years volume of space. And that's called a cluster of galaxies. And galaxies tend to cluster together. They're not just randomly, smoothly distributed throughout space. The other thing to note about galaxies is that they are filled with what's called dark matter. And we know this because we can stars. So galaxies like this one are actually rotating, and if they're at the right inclination, we can measure how fast the stars in the galaxy are rotating, revolving around the center. And what we find is that these stars are moving very rapidly, so rapidly that if we just looked at how much gravity there is from all the other stars, it's not enough to hold these rapidly moving stars together. They should be flying off into space. So there must be something else holding these galaxies together, something we can't see that's not the stars. And that something else is what we call dark matter. And it's dark because we can't see it. It doesn't shine light, it doesn't emit light, it doesn't interact with light. And so galaxies, it turns out, actually most of the mass in a galaxy like this one is not in these 100 billion stars. It's actually all the dark matter that surrounds these 100 billion stars. So the stars are just kind of a small
Question.
Yeah.
You said dark matter is within the galaxies.
Mm-hmm.
Is dark matter also between the different galaxies?
Yes, there is some dark matter between the galaxies as well. So like here, this is a cluster of galaxies. Each of these things is a galaxy. It has some dark matter in it. But then this whole region has a kind of blob of dark matter around it too.
Yeah.
How do you measure that?
By looking, well, in this case, so in an individual galaxy, what we do is we see how fast the stars are revolving around the center. For the whole cluster, we can measure how fast these galaxies are moving around within the cluster. And again, they're moving too fast compared to all the mass that I can add up just in the stars and the galaxies. So there must be this blob, what we call a halo of dark matter, which is holding this whole cluster together. And that was actually the first discovery of dark matter in the 1930s by the Swiss astronomer Fritz Zwicky, looking at a cluster of galaxies like this and noticing that the galaxies were just moving around too fast. Okay, so you can think of galaxies, the stars in a galaxy as like little sprinkles on this dark matter ice cream cone. Except the sprinkles are embedded within the ice cream. So it's like when you go to the fancy ice cream place and they fold the sprinkles in. Instead of just putting it. Okay, so that's dark matter. So what is dark matter? The answer is we don't know. We know what it's not, though. We know it's not ordinary. It's not normal matter. It's not the stuff that we're all made of, that our world is made of, which is atoms. right? So we're all made, the world that we see around us is made of atoms, and more fundamentally, you get down to quarks. So this is normal stuff, and we know that whatever the dark matter is, it's not made of all the stuff that our world and everything we see is made of. So it's not normal matter, because you could have imagined, well, maybe there are just, say, very, very, very faint stars, which just emit so little light that they look dark to us, or maybe very faint planets that don't shine. Couldn't those be the dark matter? And the answer is no, they can't, because we actually know how many atoms there are in the universe, and there just aren't enough to add up to make all the mass that we see around these galaxies in dark matter. So there must be some other sort of matter that's not made of atoms that's making up this dark matter. We don't know what it is. Our current hypothesis is that it's some new form of elementary particle that we've never seen before. And so physicists, are now doing experiments around the world to try to search for these dark matter particles. Yeah.
I'm just wondering how you know how many atoms there are in the world. How do you measure that?
Yeah. Good question. I was trying to skip over that. So, well, you just go out and count them all. No. So there's several different ways we know how many atoms there are, but basically, let me see. So the simplest, so basically, so we know, so the universe is made up of elements, right? There's a periodic table, right? Hydrogen, helium, and then something beyond that. I forget the, yeah. Anyway, hydrogen, helium, lithium, thank you. And metals, yeah. Everything else in astronomy, everything beyond helium is called a metal. So what we know is that actually, and I'm going to get to this, so in the Big Bang, about 3 minutes after the Big Bang, there were nuclear reactions that cooked basically reactions between neutrons and protons that started to make light nuclei like helium and lithium and some other ones. And so that those nuclear reactions took place for just a couple of minutes, and then they were done. We know a lot about the universe at that time, and so we can actually predict how much helium and lithium and other stuff was made. And then all the heavier elements were made in stars much later in the universe. And so by measuring how much, say, hydrogen versus helium there is in the universe, that actually gives us a very good handle on the density of atoms, or more precisely of protons and neutrons, which are the things that make up atoms, is in the universe. And that density is just too low by a factor of 30 or so compared to what we need for all the dark matter. So, but good question. Okay, now we get my toes. I can't skip over anything. Okay, so the dark matter may be a new kind of elementary particle. So particle physicists who wear funny hats and gloves are doing experiments around the world to look for these particles. Basically, the idea is that these particles, which may be, say, 10 times heavier than a proton, but which don't interact with ordinary matter or light like a proton does, would be zipping around through the galaxy, and occasionally they would bump into a nucleus in one of their detectors, and if it's deep underground, shielded from everything else, you can actually detect that collision. So far, no. Well, there have been some claims by some experiments that they've seen such particles, but other experiments haven't. So right now, it's still kind of up in the air.
Why do they assume they're particles and not energy waves?
Well, particles and waves are sort of two different sides of the same coin in quantum mechanics. But we need it's most useful for this purpose to think of them as particles. Yeah. Another possibility for finding dark matter is that we may actually produce it. Right. So these experiments here are looking for dark matter particles zipping around the galaxy that are holding our galaxy together. This is a big experiment, the Large Hadron Collider. This is the thing that discovered the Higgs boson that got the Nobel Prize this year. They're colliding protons with each other at very high speeds, and there's a chance that occasionally those collisions might produce one of these dark matter particles, and they would detect it. So far, they haven't found it yet.
Which sensor is that?
This is so there's two experiments, one called Atlas and the other called CMS. I don't remember which one this is. So this is deep underground, under Geneva. It's a big tunnel that goes around Geneva. Okay, fact number 4. This is all still the intro. So let's see. So the universe it's old, it's big. What was the third one? Dark, lots of galaxies. Fourth one is the universe is expanding. We've known that since the 1920s. Basically, when we look out at galaxies, they're almost all moving away from us. And if I went to any other galaxy, I would see all the other galaxies moving away from it. And so from that, we infer that the universe as a whole is expanding. That is, the distance between galaxies is increasing with time. So we've known that since the 1920s. And then if you just run this movie of the expanding universe backwards, right, eventually, if you go far enough back in time, everything will be on top of itself. All the galaxies will be on top of each other. That's what we call the Big Bang. And that's this thing that was 13.8 billion years ago. So the Big Bang really just means a period when everything was on top of each other with densities and temperatures approaching infinity. Okay. So again, what we mean by the expanding universe is that the distance between, say, pairs of galaxies is increasing with time. They're moving away from each other. So a galaxy that's about 100 million light years away from us today is moving away from us at 2,000 miles per second. So a second from now, it'll be 100 million plus 2,000 miles away from us, etc. Actually, 100 million light years plus 2. Anyway, you get the point. I'm not going to convert the units here. So galaxies the universe is expanding. The point is that galaxies themselves, our Milky Way galaxy is not expanding. Galaxies are held together by the dark matter. So our galaxy is not expanding because it's collapsed and it's got so much dark matter that it's just sitting there. But the neighboring galaxies are moving away from our galaxy. Okay. So that was fact number 4. So once you start talking about the expanding universe, people start trying to visualize it, and that's where you run into trouble. Because we tend to think, especially the word Big Bang, you tend to think of an explosion. When we think of explosion, we think of something exploding outward into empty space. So that's not what we think is going on here. The universe doesn't have a center. There's no one place where the Big Bang happened. It happened everywhere. And it's not, we don't think it's expanding into some pre-existing empty space, right? The space itself is expanding. Right, so don't think of it as some explosion, just think of it as space itself, galaxies moving apart. What else? Right, and so, again, if we run the movie backward in time, the universe initially was very hot and dense. Today, it's relatively cold and diffuse. So the distance between galaxies is very large. Typical distance between nearby galaxies is a few million light years. And the universe today has a temperature that's about 3 degrees above absolute zero. Okay, so just to fill in, flesh that in a little bit. So this is a picture of the universe when it was about 400,000 years old. This is from a satellite called the clump satellite, which just finished operating. So this is actually a map of the temperature over the whole sky. And regions, basically everywhere the temperature is about 3 degrees above absolute zero. But here it's 0.0001 above 3, actually 2.7, and here it's 0.0001 below 2.7. So basically, the universe at this early time was nearly uniform and had just very tiny ripples in its temperature or its density. So that was what the infant universe looked like. Today, the universe looks like this. It's filled with these billions of galaxies. It's much lumpier. There are regions. These are clusters of galaxies, large agglomerations of clusters. It's much lumpier than it was just a few 100,000 years after the Big Bang. And so our picture of how we got from that first map to the second map is here. So this is a movie of a simulation made of how galaxies form over cosmic time. And basically what you put in is a universe that's expanding, that has gravity, that traps things together, and that has dark matter. And what you see, and I'll just run it again, is you start with a universe that's nearly smooth and homogeneous, and then over time, those small initial ripples grow to form galaxies, clusters of galaxies, etc. And it's just gravity that's doing that work. Gravity acting on these swarms of dark matter particles. And this simulation, in fact, they didn't even bother to put atoms into the simulation. There's no sprinkles. This is just dark matter. And yet you end up with a universe that looks both qualitatively and quantitatively very much like what we actually observe with galaxy surveys. Right, so the picture we have was about 13.8 billion years ago. The Big Bang, initially, it was quite nearly homogeneous. There were small ripples that we see in this background radiation. Those ripples then grew by gravitational instability to form these billions of galaxies that are all surrounded by halos of dark matter today. Okay, so that's what every person should know about. Okay, that'll be a quiz. Okay, so now things get more interesting, and I'm now getting into what my area of work is. So we know the universe is expanding, so it's natural to ask, as the universe evolves, what happens to that rate of expansion? Do we expect it to be always expanding at the same rate? Should it be getting slower, faster? What do we expect? And the expectation, again, gravity is the dominant force on large scales in the universe. And everything, feels gravity. So all the galaxies over in this part of the universe and their dark matter halos should be attracting all the galaxies in this part of the universe. So even though they're moving away from each other, you would expect that they would move more and more slowly as time goes on because they're tugging at each other. Galaxies over here are tugging at things over here. So you expect that as the universe expands, it's initially expanding very rapidly, but then would slow down over time. So that's what you would think, that's what you would expect. But in fact, that's not what we find. So 15 years ago or so, two teams of astronomers instead found that the universe, the expansion is speeding up. It's getting faster than light. So that is, if I look at this particular galaxy, it's moving away from us at 2,000 miles per second. If I came back, 10, 20, 100 years from now, its speed relative to us would actually be a little bit bigger than it was when I first measured it, instead of smaller. And so this was a big deal. And so 2 years ago, they got the Nobel Prize for this. And so what they actually did is they were observing supernovae. These are stars that explode. They come to the end of their lifetime. And they become, for a period of a few weeks to months, as bright as an entire galaxy of billions of stars. So this was a supernova that exploded in 1994. So before it exploded, it was fainter than actually, it was as bright as a typical star like the sun. When it reached its maximum brightness, it was billions of times brighter than the sun. So there's a lot of energy in there. And the point is that there are certain types of these exploding supernovae that when they reach their peak brightness, they're like 100-watt light bulbs. They're much brighter than 100 watts, but they all have the same brightness, the same wattage. That means if you know how bright something is, you can tell how far away it is, right? Something twice as far away should, if it has the same wattage, it should be 4 times fainter than something nearby. And so that's what these astronomers did. They measured actually tens of supernovae, and found that they were the distant ones were fainter than they expected, and that was the discovery of cosmic acceleration. So this is just a gallery of several hundred supernovae that we measured a few years after that in a different survey. So each little blue blob here is one of these supernovae that explode and becomes bright for a period of a few weeks and then fades. And so now, with much more data than they had in 1998, we've confirmed and have kind of made more precise this notion that the universe is really speeding up. So why is this? Why do we call this a mystery? So the reason we call this a mystery. Does anyone have So the reason we call this a mystery is, so if I take any ordinary object and I throw it up, as soon as it leaves my hand, it starts slowing down, right? So I impart an initial speed to it, but as soon as it leaves my hand, it feels gravity towards the center of the Earth, slows it down, eventually stops it, and makes it come back to Earth, right? And every time you've thrown up a ball or whatever, that's always what's happened. Anytime anyone has ever thrown up a ball or any kind of thing, the same thing has always happened. You hit a home run, same thing happens. But the universe isn't doing that. So what's effectively happening with the universe is you throw the object up, it initially starts slowing down because of gravity, but then while it's still going up, but slowing down, it suddenly starts speeding up, and then just takes off and would like zoom out of the atmosphere into outer space. Okay? So we've never seen that happen before. At least I haven't seen that happen. But that's what the universe is doing, right? The universe, we actually think, was initially slowing down for about 5-6 billion years, but then it started speeding up. So that's not something that happens according to the usual laws of physics. So there must be some new phenomenon in nature which is causing this. So there are two things that can be going on. One is that the universe is filled with some new form of stuff, which doesn't make things attract. It actually somehow makes things repel from each other. You might call it anti-gravity. And that new stuff, we give it a name. That's what we call dark energy. So dark energy is just the name for whatever fills the universe and makes things repel each other rather than attract each other. Now, clearly, the first thing we already immediately know is that dark energy isn't very important here, right? Because every time I do this, right, it always comes back. So dark energy isn't really playing much of a role here. This is just ordinary gravity with ordinary atoms. So whatever dark energy is, it's only acting on very, very large, it's only important on the larger scales of the universe. So that's one possibility, is that the universe is made up of, and in fact about 70% of the universe is dark energy, about 20% would be, not 25% would be dark matter, and then 5% would be atoms. Yeah.
I'm sorry, we're really talking about dark matter, and now you're talking about dark energy. You just said something about the two of them.
Yeah, and I'll come back to that in a second. So that's one possibility. The other possibility is, so again, this thing comes back to Earth because of gravity, right? Because of Isaac Newton. It could be that maybe when we get to really, really large scales in the universe, our theory of gravity just breaks down. When we get to big scales, we rely on Einstein's theory of gravity, and so far that's done great. But maybe on the really, really biggest scales of the universe as a whole, Einstein's theory just breaks down. And maybe somehow gravity gets weaker, and that could cause the universe to speed up. So that's another possibility. It's either dark energy or something strange going on with gravity. So the sixth fact about the universe that we conclude from this is that, in fact, as I just said, 95% of the universe is dark. So again, 5% is ordinary matter made of atoms and stuff, and then the rest of the 95% of the universe is dark. So I like to say we are the 95%. And unfortunately, I've been arguing that the funding for our research should be proportional. Somehow they haven't given us 95% of the funding. All right, so again, 95% is dark. We think about 25% of the universe is this dark matter. That's the stuff that may be a new elementary particle that holds galaxies together. And then about 70% could be this dark energy, this gravitational repulsive stuff that speeds up the expansion of the universe. Yeah.
When you say like 5%, what 5% by what? By mass, by volume?
By mass, yeah. By mass, yeah. Or energy, which is the same thing.
So is gravity then, like, where would gravity fit in that chart? If dark energy is the opposite of...
Right, so gravity is a force,
Yeah.
right? So this is stuff.
Okay.
And
that's
then
all I
forces
just-
act between stuff. Yeah. And so gravity doesn't have mass, right? So there's stuff and then there's forces that act on the stuff. So gravity is the dominant force that acts on constituents in the universe on the largest scale.
But the dark energy has mass.
The dark energy has, yes, it has
Okay.
mass or energy, right?
Okay.
Yeah. Okay. So what is the dark energy? We don't know. That's why I'm in this field. So the most conservative hypothesis is that dark energy is actually the energy of empty space. So imagine I took this cup, I sealed it, hooked a vacuum thing to it, pumped out all the atoms, all the air, all the molecules, and could shield it from any other molecules and atoms and stuff coming in. Then I would have really empty space. And in classical physics, if there's no particles in here, there would be no energy. There would be no mass. In quantum physics, though, even if I have no real particles in there, there's still energy there. And in fact, the energy of empty space in quantum mechanics, has the right kinds of properties to be dark energy. It would be this gravitationally repulsive stuff. So that's kind of exciting. And that's actually an idea that goes back to, in some sense, to Einstein and to a Belgian astronomer, Georges Lemaitre, who was actually a priest. The problem is that when you actually calculate what the energy of empty space should be in this class, it's infinite in quantum theory. So that's not a good answer. So this is wrong. And so what physicists tend to do is say, okay, infinity was the wrong answer, so the right answer must be 0. Which isn't logic isn't always the best. So anyway, so that is a possibility that for some reason there's a very tiny amount of energy in empty space, even though we expected there to be many orders of magnitude more. But there are other possibilities as well for what the dark energy could be. And so to my mind, this is really, it's an empirical question. We need to do new kinds of experiments to try to determine the properties of dark energy and to get some idea of what it could be. Why should you care? Well, there are a couple of reasons that I care. I think one is that whatever the nature of the dark energy is, whether it's the energy of the vacuum or something else, it's going to determine how the universe evolves from here on out. The dark energy is now 70% of the universe, and it's an increasing fraction of all the mass and energy in the universe as we go forward in time. So whatever the properties of dark energy are, it's going to determine where the universe goes from here on out. So that's one reason. Again, it's 70% of the universe as a whole. Right in this room, dark energy is negligible. So its effects on Earth or even within our galaxy can't be measured. The second reason is that it's 70% of the universe. I think we should try to figure out what 70% of the universe is. And it turns out that by mapping out the universe, we can actually get clues as to the nature of the dark energy. And that's where my project, the Dark Energy Survey, comes in. So I want to spend the rest of the time talking about this project and what we're trying to do. Yeah.
Question.
Yeah.
What is a multiverse, and how would you diagnose the condition of the proponents of multiverses?
how would I diagnose the conditions of the
I'm
components?
being sarcastic.
Okay.
I'm barely reading at grade level, and I've had small glimpses of something called the multiverse.
Yeah. Okay.
Should I be scared of this?
I wouldn't be scared of the multiverse. I would maybe be scared of the proponents, but yeah, I was hoping to avoid the multiverse. So, can I come back to that afterwards? Let's come back to that. Yeah, that could take a while. Okay, and I'm on a roll here with dark energy. So, Dark Energy Survey, it's a big international collaboration of about 300 scientists from around the world, United States, Europe, South America. And we've basically built a camera and have put it on this telescope. So this is the same thing I showed at the beginning. So this is a telescope down at a place called Cerro Tololo. It's on a mountaintop about 7,000 feet above sea level in the Chilean Andes. Each of these domes houses a telescope inside it. Ours is the biggest one here, and this houses a telescope that has a mirror that's just over 4 yards across, 4 meters across. So that's what we're using to carry out this project. So this is what we actually built. This is a camera. It's a digital camera. It's kind of like what's in your iPhone, but much bigger and more expensive. So this cost about $50 million or so to build. And this is actually pretty much the real size of the camera. So your iPhone has a digital SLR has a focal plane about this big, and this is actually the real size of the focal plane. So it's big, 570 million pixels, which today doesn't sound like so much. Your iPhone probably has about 10 million or so these days. But these are very special pixels. They're very sensitive because we're looking at the dark sky. There's very little light from these distant galaxies, and so we really need to cut down any sort of noise from any other sources. And so, in fact, this is cooled down to very low temperatures, so to get rid of lots of noise. Whereas with your iPhone or your digital SLR, there's so many photons of light coming into, even when you're shooting at night, that you don't have to worry about that noise. But here we had to, so this is that makes it challenging. So this was installed on that telescope a year ago in September, and then just 2 months ago, at the end of August, we started our survey. It's going to take 5 years, and over that time, we're going to map out 300 million galaxies, and we're going to discover several thousand of these supernovae, these exploding stars, and use both of those to try to understand why the universe is speeding up. So I just want to say a little bit about the project. So this is what the actual focal plane, what the actual camera looks like. So these are called CCDs, charged coupled devices. So it's similar to what you have in your iPhone or your digital SLR. And then just like a digital SLR, there's a bunch of lenses in front of the camera that focus the light onto the camera itself. But again, these lenses are bigger than what you have in your iPhone or in a digital SLR. The biggest of our lenses is again about 1 yard across. So it's big. And then here it is actually on the telescope. So this is now inside that dome. I showed you the outside of that dome before. This is now inside the dome. So the actual telescope structure is here. This thing down here is actually this 4 yard wide mirror. And then our camera is all this stuff here. And basically the camera is pointed down at the mirror. So basically light comes from the sky, bounces off this mirror, and then goes up through these lenses to the camera. So the camera is actually not looking up at the sky, it's looking down at the mirror. So the camera itself is here. The lenses you can't see, they're behind all this black stuff here. And then this is just a whole bunch of electronics and things to control the camera, to read it out, control its temperature, etc. So again, this was all as of about a year ago. So on September 12th of last month, this is maybe where we should dim the lights.
You guys have the lights?
Much better. Great. So on September 12th last year, we took our first images of the night sky with the camera. So there are actually two reasons why we didn't do it on September 11th. Does anyone know the second reason?
It's cloudy.
Well, that actually would have been a reason, but it wasn't. No, so September 11th was also the anniversary of the coup de Allende in Chile. So it's a politically sensitive date in Chile. Okay, we also obviously didn't want to do it on 9/11. So anyway, so this is one of the first images we took. So now you can see each of these little rectangles, if you're close enough, is one of these CCDs. And we pointed it at a relatively nearby cluster of galaxies here. So those are all galaxies. And then if you just zoom in on one of those CCD devices and then blow it up, this gives you sort of the kind of sense of the detail that we have. So this is a galaxy that's about 50 million light years away or so in this cluster of galaxies. Most of the galaxies we see, those 300 million, are much smaller and fainter than this. This is an unusually nearby galaxy, but it's a pretty picture. So here's another picture again from the camera, and again all these little blobs here, are faint little smudges, are galaxies. These things with big streaks in them are actually stars within our own galaxy, which are sort of just foreground. Just for comparison, to give you a sense of how big this thing is on the sky, this is what the size of the full moon on the night sky. So basically, when you see the full moon, then imagine our camera sort of could fit 8 or so full moons into it. So it sees a big chunk of the sky at a single point in time. For comparison, say the Hubble Space Telescope really sees a very tiny little piece of the sky whenever it looks out. But it can look very deeply with very high resolution, so they're complementary. Okay, so this is just another random image. There are about 50,000 galaxies in this particular image. I'll just zoom in on that. And this is actually a distant, if you're up front, you can see this better. This is a distant cluster of hundreds of galaxies here. This is just a galaxy that happens to be in the foreground of that same distant cluster. Here's another one. I forget what this is. This is another picture of a distant cluster of galaxies. All these faint little yellow things are galaxies in this cluster, and here's just a zoom in on that same region. And again, if you're close enough, you can see little sort of line-like things here. Those are actually galaxies. Here, I can blow it up. So these kinds of things are actually galaxies. These little smudges are galaxies that are behind the cluster. The light from those galaxies gets bent as it goes around the cluster. And so instead of seeing it as an elliptical blob, we see it as a kind of arc. And so that's the signature of what's called gravitational lensing. This is the bending of light by the gravity of these clusters of galaxies. And so we can use that bending to actually map out the dark matter. We can't see the dark matter, but we can see the effects of the dark matter on the galaxies that are behind the cluster. So here's an example of that. So the image is the image of a cluster of galaxies, and then these contours is actually a map of the dark matter in that cluster, which we can't see directly, but which we infer because it causes this bending of light of galaxies behind the cluster. Okay, this is the Orion Nebula. This has nothing to do with our survey, but it's just a pretty picture. So that was taken with our camera, so I like to show it. So this is a nearby, this is within our galaxy. One of the things we're doing, I mentioned, is looking for these supernovae. And so what we do is we go back to the same part of the sky, and we observe it every few nights. And then we compare with what was there a few nights previous. So we did that last November, and then in December, this is a picture of the same part of the sky. And then what you see is there's this new object, right, which wasn't there in November, but which is now there. And this is a supernova, a star that exploded in that galaxy. And then by going back every few nights, we can measure the brightness of that supernova and figure out its distance. So that's that. So we actually started, again, the official survey itself at the end of August. Got a little bit of press coverage, which was always nice. I'm going to wrap it up. Right, so basically the mission of this project is to probe the nature, to try to understand the nature of dark energy and why the universe is speeding up. And again, practically speaking, the way we're going to do that is by using, these supernovas to measure how fast the universe has been expanding at different times. And we're also going to map out all these galaxies and look at how their clustering changes over time. So remember I showed that movie of galaxies clumping together. As I change the properties of dark energy, that changes that movie in regular ways. And so by looking at different times in the past, we can uncover the effects of dark energy on the growth of structure in the universe. So again, in a nutshell, we're going to survey about 300 million galaxies. At the end of the day, we'll have covered about 1/8 of the sky, several thousand supernovae, and we have a couple of websites where you can go look at more of this stuff. So just to summarize the takeaway, so first of all, there's the things that everyone should know about the universe. It's old, it's big, it's filled with galaxies that are mostly dark matter. It expanded, it's still expanding from a Big Bang about 14 billion years ago. And this expansion is speeding up. We don't know why, but it may be due to this dark energy, which we're trying to understand. So I think, again, everyone from middle school and up should know these basic facts about the universe, just as you know that we have genes and there's evolution and things like that. And then with the Dark Energy Survey, with this project, we're embarked on this journey to try to address this mystery of why the universe is speeding up and learn more about the evolution of the cosmos. I just want to finish with this quote. I think, to my mind, some of this may seem very technical, but actually, to my mind, the more we understand about the cosmos, gives us, it increases our connection to the cosmos, gives us a more profound connection to it. And I like to think of this poem from Wallace Stevens, Sunday Morning, which is probably not a good poem to talk about in this context. For those of you who read it, it's sort of the canonical Death of God poem. But I think it captures, if I take it out of context, I like this phrasing that sort of, the more we understand about the cosmos, then the sky will be much friendlier than now. A part of labor and a part of pain, next in glory to enduring love, not this dividing and indifferent blue. And so I'll just finish with this image. This is taken from the observatory of sort of the mountains looking out towards the coast of the Pacific. Thanks.
If you do need to go to class, you can go that way would be great, and you knows how to submit
You had a map of the universe when it was like 4 billion years old or something?
400.
How would you take that photo? How do we know what it looked like back then?
Oh, that is a photo.
Yeah, I mean,
except blue and orange.
right, because we weren't around back then.
Oh, right. This one.
Yes.
Yeah. Right, we weren't around then, but what we're seeing is the light that's come to us from then. So as we look out in the universe, we're looking back in time, because light has a finite speed. So the farther out we look, the farther back in time we look. And here we're looking at its surface, where the light that left that spherical surface around us, it left that surface 400,000 years after the Big Bang, and it's been traveling to us for 13.8 billion minus 400,000. And we're just detecting it now.
how does that work when you said that we shouldn't think of it as a sort of linear thing, like the light coming this way, and we look in that direction and we see where we've come from?
Stretch that on a globe all around you.
That's
if
a
you
question.
looked anywhere, you would see some part of that. Take this
Yeah.
whole spherical thing and slap it on a
So this is a projection, just the way, a map of the Earth is a projection of what's actually of the Earth. So this is just a projection of the whole surface of the sky, so that we can see it on a two-dimensional image. Is that what you're asking?
Yeah, but then how would it be different from the images that you're taking now?
Good question. Okay, right. So here we're looking at light in a particular, we're looking at light in microwaves.
Okay.
And those have traveled from this very early time, essentially unimpeded to us. And so what we're actually looking, this isn't actually an image, it's actually the temperature of those photons. So it's sort of the intensity of the photons. So light in the microwave part of the spectrum reaches us from this very vast early point in the universe. Here, what we're instead looking at is this is a survey done not in microwaves, but actually in near infrared light, so closer to optical light, visible light. And here, the light's just not coming from so far, it's coming from much nearby. So most of these galaxies are, hundreds of millions of light years away. They're not. Whereas this one, I'm essentially looking out to the edge of the visible universe. This is as far back as we can look, and that's what we can do with microwave light. But with optical, which is what we're doing with our survey, or near infrared light, we're really only seeing the much more recent, few billion years of the universe. Does that make sense?
Yes.
So in some sense, this is just a much deeper slice of the universe than this one. And so this one is actually much smoother than this one because of this fact that as the universe evolves, it goes from smooth to lumpy.
Thank you.
All right? Yeah.
Does the Big Bang Theory make you a theologian who believes in creation?
It doesn't make me a theologian, that's for sure. Does it make me believe in creation? It doesn't make me believe in any particular creation myth, or what it does make me believe in is that everything in the universe that we observe had its origin in this nearly singular, very hot, dense phase. And basically, we can't, with our current understanding of physics, we can sort of extrapolate backwards to a tiny, tiny fraction of a second after a point where things were genuinely singular. And beyond that, we can't go because our theories break down. Our concepts of space and time just break down. But that's, but conditions at that point are close enough to, extreme that, yes, you can call that a creation event. Now, there's a whole question about whether, is it, so there's a question about the multiverse. Are there maybe were there multiple creation events? We don't know, or we don't have any evidence for them. What happened before this Big Bang? We can't say because our current laws of physics break down. People are speculating about extrapolating those laws of physics to something before. But so far, that's just speculation. So I believe that the Big Bang was a kind of creation event in the limited sense I just said. But I don't see a reason to connect that to, how do I say it? I think it's somewhat coincidental that has a kind of linguistic connection with what we traditionally talk about with creation. Is that a easy way of putting it? Yeah.
So I feel like in this slide particularly, the experiment is confined to a box.
Yeah, That's just, yeah.
How do you apply that to the expanding universe when it's not confined to a box?
Yeah, so good point. So it has to be confined to a box because a computer is finite. And actually this was done in an expanding universe, but you don't actually see, they've taken the expansion out. So if this was done in sort of real things, these things would be falling in, but all this stuff would be actually moving apart at the same time. But they've taken that out just so otherwise by the end of the movie, the scale would have been too different from the beginning. So what people try to do, though, is they just try to simulate, make their box big enough that it's a sort of a good representation of the universe as a whole. So it's true, there is stuff going on, in principle, out here and out here in the universe, which is affecting what's going on, near the borders of that, and that they can't account for. But if you make the box big enough, then sort of on average, those effects are washed out. Actually, in principle, what they actually can do is, through a mathematical trick, you can actually identify this side of the box with that side and that side. You can sort of make it into a torus, and then it's finite but with no boundary. And again, if you make that big enough, then we have reason to believe that we're not sort of missing stuff due to what's beyond the box. So that's a good question. So the answer is you just need to make the box as big as you can. Yeah.
So even after just 25 minutes of trying to think about numbers this big and butting up against the incapacity of at least my, or maybe y'all can wrap your head around it, but how do you, I imagine it's kind of traumatizing to constantly come up with the limitation of your own ability to comprehend what you're looking at. Like, what do you go to? I mean, are you just, is that something as a scientist that you're just better at than us? Or is it,
no.
How do you cope with it? Is it Wallace Stevens, right? Is it
we just ignore it.
Right. And that's a kind of capacity, right? Ignoring it and the ability to say, it's like being a trauma surgeon and saying that doesn't bother me anymore because I've seen a lot of guts.
Yeah.
But, what is it that you go to that helps?
Well, I think the main thing we go to is the mathematics, right? We have a mathematical description for all of this, which gives us a concrete way of describing it. Where you're talking about scales where you're right, sort of conceptualizing it in a visual sense becomes very difficult. We still use pictures and analogies, but those are limited. This whole thing of, for example, this picture. This was one representation, trying to be a representation of the expanding universe, but it's limited, right? Because in this thing, it looks like the universe is a ball expanding into some empty space, and that's not. I told you before, that's not what we think is going on. So, in some sense, we run up against the limitations of our ability to visualize or come up with good analogies. We still use those because they're still important to gain some intuition. But at the end of the day, in practice, one goes to a mathematical description, which has its own, limitations. But and then eventually you just sort of become comfortable with the mathematical description. Yeah. Also, I think just this was only 25 minutes. Right. But after several years, you do become more comfortable with things also. Actually, it's more than 25 minutes.
I think that's good.
We thank you for listening to or viewing our podcast. For more information and for other podcasts, please see our website, divinity.uchicago.edu/podcasts. Copyright, the University of Chicago Divinity School.